from algebra class that the inverse functions undo each other. That's their purpose. That's their job. For example, the inverse of x squared is the square root of x. Thus, the square root of x squared is x. The square root and the square undid each other, just giving you x. The square of the square root of x is x. The two functions undid each other and just gave you x. The inverse function of multiplying is division, because if I take a times x and I divide by a, I just get x. And if I take x divided by a and I multiply by a, I again just get x. The inverse function of e to the x is natural log of x. That's the notation that has become common to mean the inverse function of e to the x. So if you plug e to the x into ln of x, the two ideas cancel each other out and you get x as your output. If you put natural log of x as the exponent on e, you also just get x, because the idea is that the two functions cancel each other out. So really, you have to think about the idea of inverse functions. The notation is just some notation that we had to come up with because we need to communicate with some sort of language. So for the trig functions, we have cosine, sine, and tangent. Those are the three functions we're going to focus on. And the notation for the inverse function is either arc cosine, arc sine, and arc tangent, or you can use a little inverse symbol by putting an exponent of -1, but you don't want to read it as an exponent of -1. Instead, you want to read it as the notation for the inverse function. Your TI graphing calculator is going to use that as the notation on the calculator buttons. However, Excel and some other programming languages are going to use the arc notation. Again, it's made up notation to communicate to us that we're talking about the idea of the reverse function of cosine, sine, and tangent. So throughout this video and throughout our class and throughout all of your mathematics and physics studies, arc, cosine, or writing the superscripted -1 on cosine is going to mean the same thing. I will just interchange them. Sometimes I will use one, sometimes I will use the other. And just once again, the idea is that inverse functions undo each other. So arc cosine of x is x. Inverse sine of x is x. Arc tangent of x is x. Another thing to think about in terms of inverse functions are how the output and the input are reversed. The domain and range, that is, are reversed. So with the trig functions, cosine, sine, and tangent, you plugged in angles. You might have been interpreting them as angles around the unit circle, or you might have been interpreting them as angles in a triangle, but you were plugging in angles and you were getting out various ratios. For cosine, it was the ratio of the adjacent side to the hypotenuse. For sine, it was the opposite side to the hypotenuse. For tangent, it was the opposite side to the adjacent side. Or if you were using unit circle definitions, it was the x-coordinate for cosine when you rotated a certain angle. It was the y-coordinate for sine when you were rotating a certain angle. And for tangent, it was the ratio of y to x. The inverse functions are now going to have you plug in those ratios, and you get out the angles as your answers. So for example, arc cosine of 1/2 is either pi over 3 if you're working in radians or 60 degrees. Inverse sine or arc sine of 1 over the square root of 2 is equal to pi over 4 or 45 degrees. Arc tangent or inverse tangent of -1 over the square root of 3 is negative pi over 6 or negative 30 degrees. And that's because cosine of pi over 3 was 1/2. Sine of the angle pi over 4 was 1 over the square root of 2. Tangent of negative pi over 6 is equal to negative 1 over the square root of 3. So notice my domain and range, my inputs and outputs, have been swapped. Here is an example using a right triangle. I have a right triangle where one leg is 8 and the other leg is the square root of 336, and my hypotenuse is 20. So arc cosine of the adjacent side, square root of 336 over the hypotenuse of 20, would equal that angle theta. Inverse sine or arc sine of the opposite side 8 divided by the hypotenuse of 20 would also give me that same angle, because for that angle the opposite side is 8 and the hypotenuse is 20. I could also use inverse tangent. And if I were using inverse tangent, I would plug in the opposite side of 8 and the adjacent side of the square root of 336. By the way, if you type any of these in your calculator, and by the way, your TI graphing calculator is going to use the inverse function notation. It's going to have buttons with a little superscripted -1. You will get 23.58 degrees if you're in degree mode. Remember, throughout our whole class, you're going to have to pay attention to whether you want to be in degree mode or you want to be in radian mode. In this case, we're working with a triangle, and anytime you're working with shapes or designs, you're probably going to measure in degrees, just because as people, we usually talk about angles in terms of shapes and degrees. Like you might say, that's the slope of that road is a 12-degree angle, or the slope of the roof line is a 45-degree angle. You're more likely to talk about degrees. Now remember, cosine is the x-coordinate as you rotate around the unit circle. Sine is the y-coordinate as you rotate around the unit circle. Tangent is the ratio of the y-coordinate to the x-coordinate. So if you rotate multiple times around the unit circle, or you rotate backwards, that is clockwise, you're going to hit different angles, but you're still going to be hitting the same x-coordinates. So for example, some angles for which cosine is 1/2 are 60 degrees, but at 300 degrees, that's true. Negative 60 degrees, that's true. If I went all the way around and then went an additional 60 degrees, so a 420-degree angle, cosine would be 1/2. And if I went multiple times around and landed at 660 degrees, cosine would still be 1/2. The same could be true for sine of a number like 0.4. There are many angles where sine is equal to 0.4. There are many angles where tangent is equal to -2. So we don't want to forget this. I mean, we sometimes want to use all of these answers, but if we were actually going to define inverse cosine, inverse sine, inverse tangent as a function, we need to have a decision on what is going to be the one output. Remember, the definition of a function is you give me an input, I follow some rule, and I give you only one answer. So we have to come to some agreement on what is that one answer going to be. A few hundred years ago, when the enlightened world was working on various science and art themes, a decision was made as to what we should use as the official domains and ranges for our inverse trig functions. For cosine, if you rotate a half circle in quadrant 1 and quadrant 2, you end up covering all the possible values that cosine reaches. And then after you rotate that half circle, you start to repeat those values. So from 0 to pi, or 0 to 180 degrees, is considered the official range of the function inverse cosine. Now for sine, we're going to use quadrant 1 from 0 to pi over 2, but you don't hit negative values for sine until quadrant 3. So there would be this gap in between quadrant 1 and quadrant 3. To solve that issue, if we considered rotating negative angles, if we considered rotating clockwise from 0 to negative pi over 2, I hit negative values of sine because y is negative. So we're going to make the official range for arc sine negative pi over 2 to positive pi over 2. And that way that range is all connected. And you can see that in the graph. Arctangent actually has the same range as inverse tangent because tangent reaches all of its negative values in quadrant 4 and all of its positive values in quadrant 2. So it's convenient to use from negative pi over 2 to positive pi over 2 also as the range for tangent. Now the domains are just what were the ranges of cosine, sine, and tangent. For cosine, you only got values out between -1 and 1. Same with sine. But tangent and cotangent, remember, all real numbers were the output. So that's now our domain. Looking at some examples here, what if I wanted to find arc cosine of negative square root of 3 over 2? Where is cosine negative? In quadrant 2 and in quadrant 3. But remember our restricted range. So cosine is negative in quadrant 2. We're going to use those values because the restricted range went from 0 to pi. So 5 pi over 6 is the official function answer for arc cosine of negative square root of 3 over 2. So what about arc sine of -1/2? Where is sine negative? Quadrant 3 and quadrant 4. But remember, if we use the angles in quadrant 3, there was that gap between where sine was positive in quadrant 1 and where sine became negative in quadrant 3. We created a connected range by using the negative angles rotating clockwise into quadrant 4. So rotating backwards or clockwise, arc sine of -1/2 is negative pi over 6. Now for tangent, we are also using quadrant 4 and quadrant 1. And if I wanted to find arctangent of -2, that's not one of our nice angles that we have memorized. So I use my calculator, and my calculator gives me approximately 0.6747. So that's an angle in quadrant 4 from having rotated clockwise. There will be plenty of times where we want to work beyond just the restricted answer that our calculator gives us. For example, here we have low temperatures of St. Louis, the normal low temperatures, and obviously there's two places where we hit the line of equilibrium. Pick pretty much any temperature between 21 and 71, and you're going to find two different times in the year where you hit that normal low temperature. So the restricted range answer just gets us started, and then we need to understand more deeply about our trig functions to get the other answers. We will spend a lot more time on that subject when we actually get into solving equations, but I just wanted to mention that you're not always just going to restrict yourself to the one answer that your calculator gives you. Let's consider a few other examples. Inverse cosine of 11 pi over 6. Now it'd be very tempting to say, oops, inverse functions, they cancel each other out, so my answer should be 11 pi over 6. But 11 pi over 6 is not in the official range of inverse cosine. So cosine of 11 pi over 6 is the square root of 3 over 2. So really I'm asking, what angle gives me a value of square root of 3 over 2? Well, pi over 6 is an angle that gives me cosine equal to square root of 3 over 2. So pi over 6 is in the official range of inverse cosine, and that should be the official answer. Now, what if I was considering inverse sine of cosine of 11 pi over 6? Remember, cosine of 11 pi over 6 is the square root of 3 over 2. So this is asking, what is inverse sine of square root of 3 over 2? Well, what is inverse sine of square root of 3 over 2? Oh, it's 60 degrees, or pi over 3. So we're going to answer pi over 3 because we're asking, what is the inverse sine value of square root of 3 over 2? It just happens that cosine of 11 pi over 6 is square root of 3 over 2. Now, what if I was asking, what is tangent of inverse cosine of 1/5? Now, that's not one of my nice angles, so I can't just, think about my unit circle values that I've memorized from earlier, or thought about enough that they almost seem like they're memorized. Instead, I want to draw a right triangle. And the definition of cosine is that it's the ratio of the adjacent side to the hypotenuse. And so I draw a right triangle whose adjacent side is 1 and hypotenuse is 5. And then I figure out what the other side would be. So I use Pythagorean theorem. So 1 squared plus the other side squared would have to equal 5 squared. So solving that for the other side, I get that the missing side had to be the square root of 24. So the missing side, square root of 24, the opposite side. So tangent of that angle is the opposite side divided by the adjacent side. So the adjacent side is 1, and so tangent of inverse cosine of 1/5 should be the square root of 24 over 1, or the square root of 24. The purpose of this video was just to give you an introduction to the inverse trig functions, to talk about the official ranges, and to look at their graphs, and to look at some example problems. So we've only sampled a little bit of the uses of the inverse trig functions. We'll be seeing a lot more of them. For those of you who watch The Big Bang Theory to read the commentaries at the end of the show, this is what he'd say about rationalizing denominators. Yes, I know the book has square root of 2 over 2 and not 1 over the square root of 2 for the values of sine and cosine of 45 degrees. I know the book has square root of 3 over 3 for cotangent of 60 degrees, not 1 over the square root of 3. All the book has done is taken the accurate values of 1 over the square root of 2 and 1 over the square root of 3 and rationalized the denominators you learned how to do in algebra class. Is rationalizing necessary? No. Does it make square root of 2 over 2 and square root of 3 over 3 more right than 1 over the square root of 2 and 1 over the square root of 3? No. If you like rationalized denominators, then rationalize your denominators, but at least be consistent about it. If you want to write square root of 2 over 2 for the value of cosine of 45 degrees, don't write the value of secant of 45 degrees as 2 over the square root of 2, because if you were really into rationalized denominators, why would you write 2 over the square root of 2 rather than the square root of 2? It just makes it look like you really don't understand why the value of cosine of 45 degrees is square root of 2 over 2, but instead you just got the value out of the book. You at least did learn the definition of secant, which is why you wrote 2 over the square root of 2, but you really only understand half of what you're doing. That is what it looks like. So rationalize your denominators. If you're afraid that Systemary Oldfart is going to wrap your knuckles for not rationalizing your denominators, but be consistent about it, because if she would probably wrap your knuckles also for writing 2 over the square root of 2 and 3 over the square root of 2 versus square root of 2 or square root of 3.